recording. If you can hear me, clap. 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 Yeah, everybody hears me now, right? So welcome back to our second talk from Australian Club. Woo! So I think I already explained what Australian Tap was. Was anyone new here and doesn't know what Australian Tap is? Yes? Okay. Okay, so the basic idea is it's an international organization that started in New York and spread out like a virus all around the world. And it's just a way to approach science to the general audience, having fun, and what better place to have fun than a bar with drinks. So yes. And you can follow us, Australian Tap Paris, AOT Paris, in many social media. Also, we have our own website, that's in QR code. But most importantly, if you have any feedback, we always want to improve. We're scientists. So send us an email at aotparis@gmail.com or just follow that QR code. And if you're all happy with that, there is a problem with the presentation. Okay.
I'm not sure.
Okay.
Can you see with the slide?
Yeah. Okay, maybe? Wait. We have technical problems to resolve it in 5 seconds.
Oh.
Better?
It depends on the slides. No, here you
Okay. Okay. Let's see.
It depends if you have a.
Let's see.
Take fine. Take fine when I.
Okay, I'm pretty sure our next speaker is smarter than this aspect ratio and it will look much better. Okay, so we are going to have a talk. We had a talk in the past about how stars were born, and now we will know how they will die in a very special way. So stars explode. Oh, ooh la la, ooh la la. Okay, so Matteo Bugli is Italian now. Bravo. He works in the Institute of Astrophysics. But he's a postdoc, so he is a doctor. Okay, and then he got his PhD in the Max Planck Institute for Astrophysics in Munich. Cool place. He studied accretion disks around black holes. Ooh. Trou noir. What? Is that right? No? Trou noir? Yeah. That's supposed to be French. So he has been a postdoc in CSA Clay, the University of Turin, and he works on massive star explosions. Okay, you have a hint about what he's going to talk about. Relativistic jets, wow, and the dynamics of magnetic fields and extreme environments. And in his talk, he will say many things because I don't want to spoil anything. So help me to welcome Dr. Matteo Bugli.
Thank you, Sophia, for the very nice introduction, and thank you everyone for being here. Thanks. Is it fine? Can you hear me well? Should I
Yeah, that's perfect.
Okay. I will just stay very close to the mic and just approach the laptop. All right. So once again, thank you everyone for being here. I'm Matteo Bugli, and it's a real pleasure to be here. So first thing first, I would like to share with you the fact that I took to heart the old format of astronomy tab. So I took care of putting some tab in my astronomy. So I'm a second point. So please be kind, and whether I make a fool out of myself, please have some tolerance for that. Second part of the evening, we have heard from Ugo actually how stars are born, how they come to our universe, and as all good things, I mean, we know that they must end at some point. So I will talk to you about what comes at the end of the life of a star, and there's a simple line in this story because actually lots of interesting things happen, and as I will show you, I mean, ends can be new beginnings in other forms. So I will try to cheer you up and not just linger in the old death part of the talk. So let's begin with this picture that I used just on my chance. What you're seeing is the so-called supernova remnants. So we're looking at Cassiopeia A. This is the rest what actually ended up remaining after the explosion of a star. So this is one of the so-called historical supernovae. Has been observed plenty of times with plenty of instruments. And you can see that these bright colors are actually a composition of different wavelengths from different instruments. So with our naked eye, we cannot see how beautiful it is, but if we actually take the extra mile to actually use instruments that can see what we cannot see with naked eye, this is what we get access to. So Hugo has presented some images with the James Webb Space Telescope. This is one example of what the JWST can do. This is this image of the same supernova remnant, and the amount of detail, the structure that we can see is just baffling, mind-boggling. You can see all this turbulence happening, all these filaments, all these structures, and this is something that you can actually see, so it's out there. And if we actually look at different wavelengths, things can get even more complex, more interesting. This is an image on a slightly longer wavelength with the same instrument, just the same telescope with different instrument. And you can see how we have these, it's called green monster. We have these filaments, these structures. They are trying to tell us a story. So they're trying to tell us what actually happened, how we got there. And the thing is that we need to be clever in order to actually figure out how we got to that point. This is another competition. On top of that, we overlay data from X-ray telescope from Chandra and even different structure actually here. And overall, we know that in the kind of centuries, humanity has observed supernovae even without fancy telescopes, just because they are so energetic, so bright, such bright events. So this is a sample of so-called historical supernovae, and these are rests of explosions that people have seen with their own eyes without any telescope throughout the history of humanity. And most of them are actually formed and due to the explosion of massive stars. Some of them are due to the explosion, thermonuclear explosion, so-called type 1A supernovae. But what I'm going to talk to you about is the explosion that happened when you have a massive star, massive meaning many times, at least 8 times the mass of our sun, and what it happens when these stars reaches the end of its life. And the main point is to understand how these stars explode, because we see so many stars, and then we see suddenly some stars that outshine their galaxy they're in. What is the mechanism? Why do they explode? I mean, there is some underlying physics that we want to understand. So first thing first, let's talk about a massive star. Let's take a prototypical massive star, which is not the sun, because our sun is rather light compared to what massive stars look like. But let's take a star that is at least 8 times, 10 times, a few tens of times the mass of our sun. So in this case, we know that this star will not just burn hydrogen, it will pass most of its time to burn hydrogen and to give us some light. At some point, the gravity that is at the core where hydrogen is burned will become sufficiently important to make the helium burn. And so helium will produce heavier and heavier elements, and this chain of events and burning will go on up to the point where we form at the very core of the star iron or elements that are akin to iron. They are pretty heavy. At that point, fusing those elements will not be energetically favorable. So we will not get any energy out of that. So the star simply stops there. The gravity is there. So at some point, we reach a state where we have this stratified wall with denser and denser elements the closer we get to the core. And essentially, what we refer to for the stars is something like having a so-called onion structure. There are straits and straits that go in the center. And if you're familiar with some animation movies, you will recognize the stars are essentially as ogres. They have layers. And at some point, we know that the internal layers of the star it will just not be able to take it anymore. It will not be able to counteract the gravity with some burning, because it will have nothing to burn to get energy out of that. And that's unfortunately the beginning of the end. But, so up to this point, we followed the star that has formed thanks to Hugo at some point, and then during its lifetime. Well, it really depends on its mass. But the thing is that the more massive the star, the shorter its life is. Because more mass, gravity is even more strong, the burning becomes even more fast. So massive stars, they shine bright, they die young, and they leave a beautiful course behind. And what we want to understand is how that process actually happens. So we know first of all that once a star begins to realize at some point that it can no longer hold its weight, there is a huge amount of energy. We're talking about hundreds of times the energy budget that the sun will emit during its whole lifetime. This is huge, just for a single star. And all the energy is there, ready to be released in some form. And to understand why such energy reservoir will actually lead to an explosion, we can just take a look at what happens to a system where conservation of energy and angular momentum actually take place. So this is a video from Physics Girl, and what you will see are bouncing balls that individually will just bounce a little bit. But once they are on top of each other, just like those layers in our onion star, something different will happen. So basketball, blue ball, ping pong ball, but if you put them on top of each other, then the ping pong ball is just shoot up the stars. So once again, you can see that possibly, the white ball just shoots out. And this is because the inner ball, which are denser, they have more momentum, they transfer that, and that's the explosion. So in a nutshell, this is what we expect to happen during the collapse of a star. So I will take you through an animation that actually was produced in the group I was a former member of, CSFA, that shows what happens in the core of the star. The iron core of the star, the one that can no longer burn, has the size of 1,000 kilometers, more or less, or around the world. It has the mass of 1.5 times the sun, and at some point it just cannot take it longer. Gravity is just too strong, and it will start to collapse because there is no burning to keep the core on its state. So it will start to collapse, it will become denser and denser, and at some point it will reach nuclear densities. So the highest density that we can reach in the universe before creating a black hole, and at this density, the material that falls on top of the particular star will start to rebound on top of that, because the matter is so hard that essentially it can no longer compress. And at that point, we have the formation of a shock wave that starts to propagate outwards. And the shock wave is what you can think of a supernova of the stars, if the shock wave is allowed to propagate outside of the star, it is allowed to actually destroy the star itself. The main problem is that we do have, first of all, the birth of a proto-neutron star. This is a compact object. This is something which was not there before, and it was born thanks to the collapse. So we have a new object, and that object is surrounded by matter that will be falling on top of that. And the size of the system is extremely small. So a star is extremely big. I mean, our sun is a few 100,000 kilometers in radius. And a massive star can be 10 times larger or even more. And here we're talking about 100 kilometers. So it's a tiny, tiny little bit of center, which is extremely dense. But exploding is hard, this situation, because you have a whole star which is collapsing on top of yourself. The shock just can't take it. It can no longer propagate because it's losing energy. It has all the rest of the star which is falling on top of that is losing energy because it's dissociating elements. It's just not propagating any longer. So how does a star explode? The answer is comes from understanding which is the energy source that we have. So all that batch of energy, 100 times the energy of the lifetime of the sun, which is available, 99% of that is just lost in the form of neutrinos. We have electrons and protons, which due to the pressure, they just merge together, they produce neutron, but not just neutrons and neutrinos. This particle, which is not electrically charged, is not very massive, but there is a hell lot of them. And this huge plasma neutrinos is actually robbing all the energy that the star had to begin with. So 99% of the energy is lost, just gone forever. But since there is a lot of that, what if just 1% of the energy actually manages to stay in place? And in here, basically, you need to picture out the interior of the star as a star within the star. We have a system where neutrinos escape, but they escape from a surface within which they are actually trapped. So as for our sun, where photons are trapped in its interior and then escape when they reach the surface, for a broad neutron star, it's the same thing but with neutrinos. They just scatter inside, diffuse, but once they reach that sweet spot of a few tens, 100 kilometers, they just manage to escape, and then they traverse the whole rest of the star. And this is a secret to make us understood. We have this 1% of neutrinos that don't actually manage to escape and scatter from the star, but they actually interact with the matter behind the shock. They give energy, they heat up the matter behind the shock, and this is the extra push that the shock actually needs to then continue to further propagate the star. And essentially, it's a boiling pot of water which is stirred by neutrinos, which are continuously needed. Most of them are gone. Just a tiny fraction, which is enough given the flux of neutrinos, then heats up things and manages to explode the star. So the problem is that how can we detect neutrinos? Because we know that neutrinos they are not electrically charged. They're not very massive. They don't really like to interact with matter. They are just loners. They don't want to interact with anything unless there is a lot of them. So the actual way that we detect neutrinos is to use an effect that has to do with something akin to the sonic boom that we have with jets that propagate at speeds that are faster than the speed of sound. So we have this sonic boom that is produced by jets. So basically something that produces, interacts with acoustic waves in the medium by propagating faster than sound. And a similar thing happens when you have short particles that propagate through a medium which is not void, in which they propagate faster than the speed of light. So it sounds counterintuitive, but if you're not in the void, you can actually propagate faster than the speed of light. And in that case, you get the so-called triangle radiation. And this is the main principle for which we can detect the particles that are produced when neutrinos interact with our atmosphere. So there is not just one neutrinos, there's a plenty of flavors of neutrinos. There are electroneutrinos, muon, tau neutrinos, and they're all are coupled with the so-called corresponding lepton. And there's a bunch of physics that we actually do. We can understand a lot about fundamental physics if we're able to detect neutrinos. We can say something about how neutrinos oscillate within each other, because we know that flavors can change into each other from the sun. We can understand what's the ordering of the mass, which neutrinos are more massive or lighter than the others. We can also say something about whether there are neutrinos that are not encoding in the model standard, in the standard model. So, and all these from the explosion of a star. But as I said, you need lots of mass to detect these neutrinos because they are basically the ones that don't want to grab anything. So you need whole lot of matter for them to choose to interact at some point. So this is why detectors actually involve huge volume of the water or ice, where at some point you do expect a significant amount of neutrinos to interact in a signal, and then understand how where these neutrinos are coming from, how energetic they are, which flavor they are, and so understand something about what you see. So I mentioned the fact that you have this heating up of neutrinos, But this heating gap does not occur just behind the shock wave, which at some point will propagate. But it also happens within the proton core star. We have this convection, which is essentially a way to model the heating gap and the boiling the proton core star within the star itself. And so we know that there are hydrodynamical instabilities. Here I showcase the Stasi instability. Is a instability that describes how the shock reacts to the fact that there is a proton neutron star, there is matter falling. The shock is not still. It really wobbles. It really moves on a macroscopic scale. And the fact that we have these kind of motions and also motions within the proton neutron star, that means that we have very high density material wobbling around, and these screams for gravitational waves. So the gravitational waves that we have detected so far, you may know that come from extremely dramatic events, which are mergers of neutron star black holes. On a smaller scales, these kind of ripples in time and space are produced also in this case, when we have proton neutron star wobbling around, moving around. So the amplitude of these waves is expected to be smaller, but still to be significant. So close enough events is something that we can actually detect these waves. And so this is essentially a way to listen to proton neutron stars, to the explosion itself. There's gravitational waves give us a proxy to listen and see what occurs within the first fraction of a second within the star, because once this collapse happens, from the external, from the exterior, it will seem like nothing is actually happening, because this is really the most inner part of the star. A lot is happening, and the only way to take a peek at what happens in the explosion is either with neutrinos and gravitational waves, because they just don't care about the rest of the mass. They just escape the star, and they give us a way to listen or have a sense of what is happening during the explosion. And so for gravitational waves, the way that we can measure them is using giant lasers. So far we have giant lasers on Earth, which are working remarkably well. We have lasers of a few kilometers, 4 kilometers, arms, just 90 degrees on top of each other. And the principle by which they work is that if nothing happens, you expect the lasers to propagate through the arms of the instrument and come back exactly on phase. But if the gravitational wave is happening, what that means is that the two arms will sort of change with respect to each other their length. And that means that the laser will travel different lengths, and then once they get reflected from the mirrors and come back, they will no longer be in phase. So we have a signal. And this is how gravitational waves are measured. So this is the so-called multi-messenger astronomy. We have different ways to detect these events. We have a way to look at them, the photons. We have a way to sort of smell them by detecting neutrinos. And we have a way to listen to them, the gravitational waves. And all of these is telling a picture which we're trying to sort of decipher and to investigate just by looking at what the universe is telling us. So observing is not just the only way to actually understand what is happening out there. There's a way to produce experiments, but in astrophysics, you cannot really reproduce a star within the lab. Because, if we manage to do that, energy problems will no longer be an issue on Earth. And it's extremely difficult to reach that state. So the next best thing is to simulate what a star would actually look like based on the fundamental laws of physics that we know. So simulations are a fundamental tool to do that. What I'm going to show you now is the simulation of a purple-left supernova, where you can see here the proton neutron star. This is the inner 100 kilometers, and on top of that you will see material which is heated up and gravitationally unbound, so material which is ready to be ejected, colored by entropy, which is a proxy to say how warm the material is. So you can see the wobbling, this corrugated surface of a neutron star. And you have to imagine that material is involvement of that at some point material gets heated enough to actually be gravitationally unbound. And it lingers there. There is just not enough energy to propagate the shock. But if that goes long enough, then we have the expansion of the so-called ejecta. We have the beginning of the explosion, and this animation is just describing a fraction of a second between a star, and it's just describing a tiny fraction of the time in which this is happening. So if this goes well, then we actually have an explosion. In order to do the simulations, since they are so complicated, a personal laptop is not enough. So what we have to do is rely on so-called superclusters, supercomputers. You have to imagine a big room filled with basically these laptops without any screen, these black boxes that put notes, which are equivalent to a few thousand times the power that a personal laptop can provide. So with these instruments, we can reproduce in a few weeks what would take years, several years to produce with a single laptop. And this is if you don't have this kind of tool, this is a non-starter because we have so much physics to do that. And I want to remind you, it takes weeks to describe what happens in a fraction of a second. So a lot is happening in that time frame. The last thing I wanted to showcase is the fact that we have observations, we have simulations, but there are actually some experiments that we can come up with that can tell us a whole lot of what happens during a supernova. And that comes directly from the fact that if we, with pen and paper, come down to describe what is the math that tells us how this shock behaves, we can recognize that this math is the same that happens when you consider a shallow water experiment, a fountain where water is just flowing on top of the surface. And in this animation, you can see the overlay this fountain where water is falling to the center, and overlay you have the proximity neutron star at the center, and these white sort of things are meant to represent neutrinos, but in a fountain, of course, there are neutrinos. And you can see this hydraulic jump, this part where you have this foam arising. This is exactly what describes what the shock in a supernova looks like. So with this experiment, we can reproduce the dynamics of the shock. We can reproduce what the shock would do depending on the rotation that we impose to the star, depending on the size of the neutron star. And we can do that in a room. And so study the dynamics of the shock, how it rotates, its modes. And this is actually the third way that we can take a look at the explosion more or less directly. And that brings my presentation to an end. Thank you for your attention, and I'll be happy to take any questions.
Okay, so amazing talk. So who wants? Okay, for the ones who were not before, I want to encourage questions by giving you a sticker or bookmark, astronomically related, if you ask a question. So, who has a question? Don't be shy. There's no question that is not valid. Please. Thank you. Who has a question? Okay, there's one over there.
For newbie on this subject, so what do you from the star, the PMS?
So at the very center of the star, we have this.
Can you repeat the question?
Sorry, yeah. So the question is, what is this proximity neutron star I've been talking about during my talk? So a proximity neutron star represents the early stages of a neutron star. So neutron stars are these compact objects, we call them, which are what lies in between a regular star and a black hole. They're extremely dense. And they are so dense that they are stable thanks to the general pressure of neutrons and highly nuclear dense matter which they are formed of. At these stages, the proximity neutron star.
I've lost that, that's not my topic.
Sorry?
That's not my topic.
So you can think of the proximity neutron star as just a very dense part of the star, which is mostly made of neutrons, of nuclear matter. So you can think of it as something that is approaching the state of a giant atomic nucleus. So atomic nuclei are very quite ordered as matter. They're not wobbling, they're not boiling, they're very firm. In the case of a proton neutron star, temperatures are so high that the matter is in a fluid state. You have this boiling that's going on due to neutrinos. So it's a high dense matter that is not very compressible. You cannot really push it much more because it's just so dense. And so it behaves like nuclear matter, but on a macroscopic scale of tens of kilometers. And it's called proto because it's not yet a neutron star in the sense that there is all this boiling going on between neutrinos. But if we allow it to cool down, to lose enough energy through neutrinos, at some point it will essentially crystallize and it will become what we observe as neutron stars in the galaxy.
Thank you.
Oh, any other question? Oh, I see. Who was first? Be honest. Okay.
I'm asking a question again. I asked a question last time because I want a bookmark this time.
Okay.
Thank you. Yeah, but my question is in the analogy between the fountain and the shock, what is the corresponding thing in the fountain case? What is the corresponding thing to the neutrinos?
So neutrinos are not really part of the game when it comes to the fountain. So in the fountain, what you have is this water flow that is just injected at the border, and it goes down. And as it gains velocity, at some point it reaches a supercritical point where it's sort of stopped by the fact that velocities are, you have a sort of a shock in the sense that velocities are reduced abruptly. Sort of like what happens in waterfalls. You have this phenomenon where you have this rising of the water level because water can no longer go at the same speed, has to slow down, and then you have so-called hydraulic jump. So water needs to compensate for that by making a bulge out of that. So this is the analogy between the shock in supernova and the hydraulic jump in water. Like inside the fountain, you have a hole, and the hole is where the water comes down and then is reinjected. That hole represents then the proton neutron star, which is not really there. So there is no surface that is producing this wobbling. So in a natural star, exploding star, what happens is that you have the external shock, you have the inner boundary of the proton neutron star, and you have perturbations that are reflected and go back and forth. And the cycle is what feeds the instability that then produces these large-scale motions. In the case of the fountain, we have a similar dynamics, but it's just due to the perturbations that are in the water flow. There are no perturbations from hard surface, but you have, from a mathematical standpoint, the same equations. So we see that the experiment itself reproduces what a numerical simulation having shock between star would reproduce, and just on the basis of a similar equation to describe that. But besides that, then there are lots of things that are not the same. So in the fountain, we are 2D, we are just in a plane, whereas in supernova are 3D. In supernova, there is compressibility, whereas water is incompressible. But things work just perfectly well so as to produce the same dynamics of the hydraulic jump in 2D than the dynamics of a three-dimensional shock in a supernova. And that allows you to study the shock, but if you want to say something about everything else, so proton neutron star, what happens beyond the shock, then you need to go the extra mile and do some simulations.
But can we think of it this way, like the energy loss due to the neutrino is same as, like, kind of the same as the energy loss due to the water going in the hole, kind of?
In a sense, yeah. There is actually a cylinder, a metal cylinder, in the middle of the fountain, whose height sort of regulates to some extent the analog of the neutrino outflow. So essentially, by regulating the flow of the water and the height of the cylinder at the center, we can adjust for the same parameters as for the mass accretion of the star and the properties of the proximity for a star.
Okay, thank you.
You and I remember, yes, another question.
Thanks for the presentation. Last time I had a physics class was a long time ago. So, okay,
That's fine.
you have one force that goes as gravity, right? That brings everything together into the star itself. You have a second force, other force that pushes. Could you explain the second force again, please? And that's my first question. My second question is, how long does everything, all this process last?
So the second force, you mean during the life of the star?
Like at the end, because you have gravity that brings everything together, everything gets very dense, everything gets super compressed. But then why is pushing?
It's essentially pressure and heat. So you have the shock wave that starts to propagate, but it can no longer propagate because you have pressure of the material falling on top of gravity itself, gravity. But you also are losing energy because the material which is going through the shock robs the shock of some energy by dissociating its matter in its fundamental constituents. So if you have some iron element atom which is passing through the shock, it's basically disintegrating itself. And the energy to disintegrate it comes from, say, the shock itself, not itself. And so the shock can no longer propagate because it's just cannot take it. And in order to overcome this pressure that is pushing on the shock, you need to increase the heat. You need to have some extra energy, which does not come from the star itself, but comes from the neutrinos, which are emitted. So neutrinos are emitted because you have so much pressure that you smash together electrons and protons. And then give that into neutrons, which are just falling at the center, making a part of the particular star. And neutrinos is just escape.
The neutrinos are unimportant, are irrelevant until you get a lot of them with a lot of energy, with a lot of density.
That comes right away. Okay, right at the beginning. Well, it takes a bit of time, and when I say a bit of time, I say a few hundred milliseconds for the neutrinos to heat up things, which on astronomical scales is just nothing. It's just instantaneous. But all this explosion business happens at the very beginning in a span of a second or a fraction of that. So the collapse itself of the iron core will take a few hundred milliseconds. The formation of the neutron star then occurs, and then the shock formation and the so-called revival of the shock thanks to neutrinos will take another few hundred milliseconds. So in the span of 1-2 seconds, you have this shock that, if you are lucky enough, if you have a supernova, will start propagating through the star, and then it will take typically a few hours to days to reach the surface of the star. At that point, this is the point where you see the star explode. So after a few hours to days. But the actual explosion itself, the onset of the explosion, the trigger that makes anything go boom, is a matter of 1-2 seconds.
She's just thinking, oh, okay, oh my god, this whole table except you will get stickers. No shame more.
So my question is about exploring the idea of this event happening at a speed that is greater than the expansion of the universe. So like a traveling supernova, or even like a traveling black hole, because there's technically nothing tying them down, just the universe. So I was wondering if that happens, or if, if black holes are black, like we cannot see them, then what about a black hole just coming to us and
So when you say traveling, what do you mean?
so at a greater rate, at greater speed than the expansion of the universe?
So the two speeds that we are comparing are the expansion rate of the universe
So
and
like if you get a star that's traveling. And the speed in which it moves is just greater than the expansion of the universe. Like because it naturally expands, right? The universe.
Yeah.
So what about this process? Not in like this, but like this, so it's like moving really fast, faster than what you would expect.
But why would star move so fast?
I don't know. Like
Right.
that's
So-
my question.
So when so in these kind of explosions, we know that typically massive stars, they are very unlikely to have evolved completely isolated from the universe. Actually, more often than not, they are expected to occur in a so-called multiple system, a binary system. So when we have these kind of systems, there are dynamics that are where you have interaction in terms of the orbits of the stars, in terms of the environment of the massive star, that can have an impact on the dynamics of what remains after the explosion. The explosion itself imprints a so-called kick velocity. So the fact that we have all these instabilities occurring means that if you have ejecta which are wobbling around, that will imprint some momentum and some motion on the remnant neutron star. And this is essentially one of the key ingredients that we want to understand when it comes to this modeling, because we want to understand whether the explosions are imprinting enough velocity to the alpha objects to make them traverse the galaxy they're residing, to bring them with the velocity that we actually can observe, so-called proper motion that we can observe in neutron stars. But when it comes to the expansion of the universe, the expansion of the universe, I mean, everything is expanding in a given look. So in that sense, the star will just expand with the space itself. So on a local scale, we don't have the expansion rate that we have on very large scales.
That's why I asked it that way, because we're moving right now, so we're not static, but that's why I was like, even more speed than that.
So there is a tight connection between supernovae and cosmological expansion, in the sense that supernovae can provide a very practical way to gauge how the universe is expanding, thanks to the fact that some of them, namely type 1A supernovae, are so-called standard candles. So they shine in a way that it's basically extremely well predictable. In that sense, if we know how luminous they are, intrinsically luminous they are, we can gauge what's their distance, and that is used to infer then the expansion rate of the universe. But this is not intrinsically affecting the dynamics itself of the explosion, but it's just a proxy given where they explode for us to understand how the universe itself is expanding.
Thank you so much.
So the next one is
Thank you very much for the talk. Really interesting. Also for me, it's been a long time since my last physics lesson, so very happy about it. I was wondering maybe like, because you mentioned there was quite a few instances throughout the last 2,000 years or so where people were actually able to observe the star exploding. I was wondering how visible is that, and are we able to predict how far in advance, or are we able to predict this at all, or could it happen tonight?
Well, if there is one thing that astronomers and astrophysicists are praying for, begging for on their knees, is the next galactic supernova. So the next extremely violent event in the galaxy happening relatively close, but still not too close. Because if it's too close, it's a kind of bummer because we will just be wiped out. But apart from that, the last supernova which was the first multi-messenger detection of supernova in terms of light and neutrinos, occurred close by, not exactly in our galaxy, in the imaginary cloud, in 1987. And in that respect, there was an extraordinary event where we detected the light of the star. We actually saw the light, then we saw it explode, and we detected the grand total of a dozen of neutrinos. So that was it. So in principle, we could expect extremely massive stars undergo the light, sort of like the typical Jews like are going to explode one at some point or another. And it will be very cool. But unfortunately, it's a bit tricky to predict down to an accuracy of even tens or hundreds of years when a star will explode. So in that respect, I can tell you that we're definitely crossing our fingers for this event to occur at some point, because the vast we see a whole lot of supernovae. The problem is that we see them in other galaxies, more often than not. And as well as that, the problem is that they're just too far for us to detect them through neutrinos and gravitational waves. And that means that we cannot really take a peek at the explosion itself, but we can take a look at the light curve, we can take a look at, other properties. But in that respect, it's just a matter of be ready. We are trying to get ready for that. And when it happens, I mean, it will make many people very, very happy. And so that's all for that.
Thank you.
Just a very quick follow-up. How long ago had that supernova occurred?
So the one I was talking about was in 1987.
Yes, but how long ago had the star exploded?
So you're asking me about the distance of the supernova.
Well, yeah, the distance, I guess. But
Right, yeah. That's a good question. I think it was. I think you got me right there. I mean, it's really the distance of the.
I remember correctly, it was one of the Magellanic Clouds. Right?
Yeah.
Yeah, so it's like, I mean, 100 of kiloparsecs? In the order of hundreds of kiloparsecs, probably.
Okay.
So hundreds of light years. I don't know the number exactly. Yeah.
Thank you, Sophia.
I think. Don't believe me 100% to everything.
That sounds about right.
Yeah. So there was another question.
This is not live stream, right?
No. Oh, but I think you were first, right? You had a question? Yeah, she was first and then you were.
Just about the supernova that you were talking about. So how
Why?
also like how did the observation go? Seeing first and the process of how in advance did you know it would happen?
So, I mean, that supernova, we saw it because it happened, right? There was no precursor, there was no, we said, wow. Something just exploded. So, I mean, at some point it was detected and then everyone was looking at it. It has been looked for several years and there were follow-up observations, but there was no, I mean, people were not ready just with their telescopes ready, okay? Any second now. And this is part of the complexity of predicting when the collapse will start and when the explosion will start, because it really happens basically instantaneously with respect to the other scales that regulate how the universe works and how even observation works. Because, being able to just redirect a telescope in a span of 1 second or so is not as a task. I mean, this is a crucial part of what multi-messenger astronomy is about, because in this case, if we were to detect a signal in neutrinos or gravitational waves that something is happening, that is a smoking gun that explosion is occurring. But from the optical standpoint, from the point of view of light, we don't expect anything to appear within the first hours or so. But if you want to get ready at that point, if something happens close enough for you to detect neutrinos and gravitational waves, then everyone, and I would say that everyone will be ready to take a look at that, because in terms of how often supernova explodes in a galaxy, I mean, on average, you do expect 2-3% rate. And statistics doesn't care about how late they are with respect to your own galaxy. But odds are you should have one at some point close enough. But it's tricky to point second. It's good luck.
Thank you so much for the talk, Mr. Paul. My question is, that you said that the neutrinos, which are electrically neutral and not much massive, what information about the PNS can they give? That's the first question. And to follow up, can they give any information about the initial stage of the star?
The initial stage of the star.
The initial stage.
Initial. So neutrinos tell us a whole lot of what the process of the star is doing. And this is because essentially they really how much neutrinos we see and how the signal modulates over time is telling us essentially what the process of the star is doing at the center. So the neutrino signal that we do expect to occur is first of all a huge burst of neutrinos, which are due to the fact that as the collapse starts, lots and lots of neutrons are produced, and neutrinos as a consequence are produced as well, but they tend to then get trapped within the most dense parts of the star. At some point, when the shock propagates, start propagating, you reach a point where the shock reaches rarefied enough region where at some point neutrinos can just escape. This is when we do expect a huge burst of neutrinos. After this stage, when matter is accreting on top of the particular star, we do expect the modulations in neutrinos to tell us how matter is accreted on top of the stars, but also how the particular star is boiling, because these motions with the particular star can be directly connected to how neutrinos are emitted. So, in a sense, understanding neutrinos tells us what the neutron star looks like, so we can sort of put constraints on what the mass and the radius of the particular star is. But we can also tell us a lot about the dynamics of the shock itself, because this wobbling of the shock has an impact on how matter is accreted, and therefore has an impact on how neutrinos are accreted. Because the more mass you throw at the particular star, the more neutrinos are produced. And so these modulations that we could see can be a direct consequence of the instability and dynamics of the shock. So it's really something like looking at what occurs at a particular star. But the most important thing is that we do not need to forget about gravitational waves, because they also carry lots of information, and they can be very complementary to what neutrinos are doing. So putting together neutrinos and gravitational waves can tell us a whole lot more than what the individual signals per se are telling.
Okay, is there any other question around? Okay, so I think you also owe us answer what your shirt is, because I saw it close by, and I think it's very proper for this particular moment.
Yeah, I thought it was self-explanatory, but essentially, the shirt states, I don't know if everyone can say that I only drink beer on days that ends with Y. And I must say that this is actually a shirt that I got during a scientific event, a conference in South Korea, where I helped the social evening events where we facilitated the mingling of people through alcoholic beverages.
It's
But-
quite generous. I mean,
Right.
is the days of the week in Korean also with a Y? It only works in English.
I think they, even if there were days that do not end with Y in Korean, they would not acknowledge that. At least they did know during the time there.
Why not?
Yeah.
So let's thank the speaker again.
Thank you.
Okay. So that's the end of the talks. Can you go back to the slides, actually? To my slides? Yes. So are they updated, hopefully? Okay. No.
Are there more?
No, I just want to update it. Here. There's one very last thing to say, and the internet is slow. No.
Should I hit the hotspot? Should we work? Yeah.
Okay. Just this. Okay. So this is very new. We have a WhatsApp group It's free of spam, I promise you, because I'm the admin. Okay? So only admins are allowed to send messages. So if you want to follow up our next events or any astronomical important stuff that may happen in the world, you can just QR code this link and follow us in our WhatsApp group. And you will know when the next event is that we don't know yet, but we promise it's going to be as fun as this one or maybe more. Okay, so thank you so much for being here. Let's thank everybody. Yes. Thank you so much for coming.